We're looking at a scenario wherein you have motion in a vertical circle. What does that mean? So basically you are rotating something in this manner in the vertical direction. So it is in the vertical direction. Can you see that? So it's moving against gravity in some portion, and some portion gravity is helping it. When it's going up, like over here, this part, here it's going against gravity, and after that the gravity will help it come down. So we are looking at such scenarios. Okay guys, so we have to figure out the expression for the velocity, the tension in the thread. Okay, so we need to figure out the velocity at any point of time and the tension that is present in the string. So with this we have different condition, like how much should be the tension so that we have the bob going round and round. Then what should be the velocity at any point of time, things like that. So yeah, first let me start off, then it will make sense. We have a bob and we have it connected to a thread of radius r. So here I've written rod, actually let me cancel that. So we have a string of length r and the center is O. So it says going in this direction. Okay, then what else? So we are looking at expression for velocity at any point. So we are going to make use of conservation of energy. Now let the object's velocity at lowest point be VL. So actually let me take it as U. So guys, first thing is we'll enable few things. So we have point say L, that's the lowest point. Point H is the highest point. Point P is any random point. Then we have theta, and then we have say a projection of point P onto y-axis, say point N. And what else do we need? Yeah, I think this is it. So let the object's velocity be u at the lowest point over here. So here the velocity will be tangential, of course, but it will be pointing to the right over here. Okay, because it's anti-clockwise. So this has a velocity of u. Let me actually reduce it. Then let v let v at an arbitrary point P corresponding to an angle theta from the vertical. So this is a vertical line and this is theta. And the velocity over here is v. Let h be the projection of point P onto the y-axis. So this will be, this length is h. Oh yeah, we're considering this as the origin. So this is at a height of h. So this is a height of h. And so this length will be, how much will that be? Can you guess? This is the radius, this is h. So this has to be, yes, r minus h. Then what else do we need? Yeah, that's it. I think we pretty much have everything. So the tension will be along the length, along the rope, and the centripetal acceleration will be pointing towards the center of the circle. And what else? We can call this as point M, the middle. Okay, so we are pretty much done with the diagram. Small things, if I keep adding, you have your diagram. Okay, now what we are doing over here is we're trying to get an expression for V and the tension T over here, let me erase this, this tension T over here, and this is R, radius R, or we can just mention it somewhere else. Anyways, I will return it. Let me not mention that. Okay, so this is the picture. So we're trying to get an expression for V in terms of H, and see, basically, let me put it this way. Before we derive and everything, let's be practical. So when I'm going up the circle, right, the effort has to be against gravity. When coming down, the gravity will help. This being the case, what do you think the velocity will be? By default, direction is changing, that we can agree. What about the speed part? Do you think it's the same? Yes, we can maintain it same, but there's so much of factors that is influencing it. The force from the thread, the gravitational pull, right? There's so many things that is affecting, and the angle at which it is, so indirectly it's that. So basically, let me put it this way, the the thread and the gravitational pull, those are the two things that is pushing and pulling and all of that. So this is making it go in a circular manner with varying speed. So this being the case, we need to talk in terms of some variable. So that variable is H and U and everything. Okay, so we are trying to get an expression for V in terms of H, U, and so on and so forth. So you'll see what exactly we are looking at. But yeah, agenda over here is to get an expression of, actually we have already put the heading. We're trying to get an expression for the velocity at any point. So we are making use of conservation of energy. This might be a bit out of syllabus at this moment of time. You might not feel it to be very convenient to learn this, but all of this law you guys know. You guys know the law of conservation of energy, right? You would have heard of that. So, and some of you might have learned it as mechanical energy. So we are making use of that. So this tells that mechanical energy for a given system is conserved. So the kinetic energy plus the potential energy at point L, the lowest point, should be equal to kinetic energy at point P plus the potential energy at point P. Remember, L is over here and P is over there. Okay, for the sake of convenience, I'll erase this in a second. Let me paste it over here. Okay, so what is the potential kinetic energy at point L? It has a velocity of u, so half mu square plus potential energy is 0, and kinetic energy at point P is half mv square. We're getting an expression for V basically, plus potential energy at point P. So potential energy at point P will be how much? If this is your 0, is at a height of h, so mg h. So what can we do over here? I can divide m with all the terms, and I can multiply 2 throughout. So we have u square minus 2gh is equal to v square. So we have v is equal to root of u square minus 2gh. Okay, so that's it. So what can you see over here? Well, it does depend on what initial velocity started off with, and then it moved on to getting influenced by gravity and at what height it is. So how does this look like? V square is equal to u square plus 2as, right? It's the same thing. Okay, so here we are moving against gravity, and so we have minus. So, and everything else remains the same. Height is height, distance, displacement. all of that. So this expression is quite simple. Next is how much is the tension in the string that has to be maintained. Of course, to maintain a consistent velocity and all of that, how will the tension vary, and that's the expression that we are looking at. So we have, actually we missed out a few things over here. I have to go back to this diagram. What is that we are missing out over here? We are missing out gravitational pull. And we have this. So along perpendicular to this is your and tangential length. Okay. So what I'm doing is I'm resolving the vector. So this is theta, by the way. So if you're not able to see that, I'll just show it to you guys. This being one line, say this is another line. This is the transversal line. So these two are your corresponding angle. So that we know as theta. So this will be mg cos theta, and this is mg sin theta. Okay, so this we need to know. Now expression for tension at any point. We need to clear this. We don't need that. How do you do this? Tension at any point. So we need to apply. Since we're looking at force, so we need to apply Newton's second law along T. T is this length. So T minus mg cos theta should be equal to m into a. So if I take this direction as positive, so we have T minus mg cos theta is equal to m into acceleration due to gravity. The combination of this will give you the not acceleration due to gravity, the acceleration that is needed for the object to go in circular manner, your centripetal acceleration, m into ac. It has to be so. Then the tension will be equal to mg cos theta plus m. In place of ac, I'm substituting it as v square by r. Okay, this expression is your v square by r. So here we can't keep it in terms of cos theta. We need to express. See guys, it's not that we can't get expression in terms of theta. We can use in terms of theta. Agenda here is to express everything in terms of h. Radius, h, u square, and g and everything. We just want it in one variable. Okay. So agenda is not to have theta over here. Express it in terms of h. That's the whole thing. So how can you do that? We need to substitute cos theta. You know what is cos theta? Cos theta is opposite by adjacent by hypotenuse. So considering triangle ONP, cos will be r minus h divided by, sorry, I kind of got thoda distracted. I had to check the door. There was someone at the door basically. So I was looking at cos theta expression. So cos theta expression, I can get it from the triangle ONP. So cos theta is adjacent by your hypotenuse. Hypotenuse is length r. So basically r minus h by r from triangle O, what is that? OPN, yeah. So we need to substitute this and we have an expression. So that is mg times of r minus h by r plus mv square by r. So here t is equal to m by r, and we have g r minus g h plus v square. Okay, again v square is another variable. It is not fixed. This is also not something that we want. We want to just purely express in terms of u, r, and h. So what will we do? We'll take 1. So substituting exponential for p square from 1, or v from 1 actually. So we have t is equal to m by r gr minus gh plus u square minus 2gh. So a bit of rearrangement, and we can see that the tension in the string is not a simple value. It depends on quite a few things. It depends on how much velocity we want at the bottom. Then we are looking at, tension at a particular point is dependent on at what height they are at, and what is the initial velocity or the velocity at the lowest point. So it depends on those factors. Okay, so you can see that m is constant technically for a fixed object mass, right? So we have m to be constant, r is constant, g is constant, r is constant, because the string length is fixed. For a given scenario, string length is fixed, g is constant, u is also constant. So h is the one factor which that if you give at this height what is the tension in the rope, we'll be able to figure out. So that's the whole agenda over here. Okay, so let's move on. So let's recap. So in the next section, we'll be looking into different cases, different points, right? At L, what is happening? At H, what is happening? So what are the other conditions needed for it to maintain certain, certain requirement and stuff? That would be the application. So here it's just an introduction to the expression for t and the velocity at a point P. So if given a point P, what is the tension in the rope thread and what is the velocity of the object? Given it has a velocity at L to be u. So all of this, quite a few other things have been given. We will use conservation of energy to figure out the velocity, and the velocity turns out to be a similar expression which we already know. Then the tension in the string, it has a weird big expression, but the derivation is quite simple. So along this length we have t minus mg cos theta, that has to be equal to the centripetal acceleration required for the object to move. So when you simplify again, here this is also an expression. Okay, so this is everything is valid expression over here, just that we are trying to use only one variable, so we are trying to get that expression. That expression is, we want the tension in the string to be dependent on, has to be a function of h. And to solve that, we take up the geometrical structure, and we are going to substitute different expressions as and when it needs, and simplify and get the final expression. So clearly the tension is a function of height. So tension is not the same in the string. So it will vary depending on the situation. Okay. So using the results what we got and the diagram and everything, we'll be looking at specific cases. You have to copy everything from the screen.